Hello and welcome to this session on electrolysis. So we're going to try and cover or as much as we can of electrolysis in quite a short space of time. So just make sure you got your phone off or not on airplane mode so it doesn't distract you, and you've got a pen and paper to take notes. If you're ready, we shall begin. So our first question is, what is electrolysis? And what we can do with any word in science is we can try and break it down and see what it's made up of. So we've got this first part that is the word electro, and then we have lysis. Electro refers to electricity, and lysis just means to split up. So when we talk about electrolysis, what we're talking about is the decomposition produced by passing electric current through a liquid or solution containing ions. So this decomposition is just breaking up or splitting up. We get an electric current, and we have a liquid or a solution containing ions. Containing ions is very, very important. These contain ions. We've got positive ions and we've got negative ions. You might remember from learning that our positive ions are our cations and our negative ions are our anions. That's stuff that you should have learnt before and remember. We'll have a little look at this bit as well later on, but talking about liquid or a solution. So liquid just means it's in the liquid state. A solution is normally something that is aqueous. That just means it's dissolved in water. You might remember from looking back at C3 and the structure and bonding that ionic compounds can conduct electricity when aqueous or liquid because the ions are free to move. So our ions here are free to move. They're not held by that strong electrostatic force of attraction. A lot of what we look at electrolysis isn't new stuff, it's just bringing together a lot of stuff we've already done. Got a picture there or a diagram there of our setup for electrolysis. We'll have a look at that in closer detail later on. So we've got some examples of electrolysis and what they split up. So if we had sodium chloride, and the thing I've missed out on all of these is the state symbols. So I'm going to put that down as liquid, my magnesium oxide as liquid, and my aluminium oxide as liquid. They can be broken down and split up into their component parts. So sodium chloride is an ionic compound. We've got a metal and a non-metal. They're bonded together by ionic bonds, so that transfer of electrons. After electrolysis, that forms sodium and chlorine. We just split it up. Our symbol equation, we have 2NaCl makes 2Na plus Cl2. Notice we've had to balance it because chlorine as a molecule or as an element is diatomic. So Cl2 is diatomic. So we've had to balance it. The same with our oxygen as well. Now magnesium oxide, pause the video, have a go at trying to work out what that's going to be. If you're watching now, hopefully you've had a go at doing it yourself. You're right, we're going to make magnesium and oxygen. If you've had a go at doing the balanced symbol equation, we'll have a look if you're right. If not, have a go at trying to do it now. Remember again though, that oxygen is diatomic. So let's see if you got it right. There we go, we've got 2 MgO, we'll make 2 Mg plus O2. Well done if you got that correct. If you didn't get that correct, go and have a look at the video on ionic bonding on the CHS on the YouTube channel, and that will give you some advice on how to work this out. Final one, we've got aluminium oxide is going to become, that's right, aluminium and oxygen. Balanced symbol equation, have a go at trying to work it out. We've got Al2O3, we'll make 4Al plus 3O2. This one a little bit harder to balance, but you do meet this later on when we look at the extraction of aluminium. So I said we'd have a look again at this setup for electrolysis. And at the top, we've got a bit of our physics knowledge here. This is a group of cells. We've got 2 cells, so this is a battery. Or it is a power pack we could also have as well. We've then got our wires. And that's kind of where our electricity stops at that point. We've then got these large grey things sticking into our solution. These are our electrodes. And then at the bottom, we've then got our solution containing ions. So have a little think about what happens with this. So we start at the battery. Now we're going through the wires. We're going through a metal wire. Our metal wires will conduct electricity because they have delocalized electrons. So we'll get our electrons moving from here. Just show them going this way. So they're going along. So we get delocalized electrons move in the wire. I'm going to write delocalized electrons move in wire. So our delocalized electrons move in the wire, and that's what allows the current to flow through there. Now obviously with a circuit we need it to be complete. We've gone through the wire, we end up in these electrodes. These electrodes are made of carbon. They're carbon in a particular form. That form is graphite. Again, with graphite, just like metals, it's got delocalized electrons. The reason why it has delocalized electrons is that each carbon is only bonded to 3 other carbon atoms, so there is 1 spare electron per carbon atom. So again, we have delocalized electrons. So our delocalized electrons can move here. So we get more delocalized electrons that are able to move. Now they want to go into the solution. Now there's no delocalized electrons in the solution, but there are ions floating around in the solution. These ions are free to move. These ions have charges. Now when we get lots of electrons moving to this electrode, we get an overall negative charge. As it's an overall negative charge, the positive ions will be attracted to it. Now our negative ions will be attracted the other way. The reason why the electrons are being pulled away from here. So our electrons can still move. So I'm going all this way. But instead they're going to go up, round this way, and back to the batteries again, so they can go round. We get this loop going on. So our negatively charged ions will move this way, towards our other electrode. Because they're all moving around, we can get electrons being lost and gained. We can get a charge going on, or a flow of charge going on, so we get a current. Now what we have is one of the things we need to learn from electrolysis is something called panic. I find it's quite useful. It's a mnemonic to try and remember what is going on. It lets us know which electrode is which. So we have the positive anode and we have the negative is cathode. And that lets us know what is happening to each one. So our positive electrode, which is the one here, will attract our negative ions, and our negative electrode will attract our positive ions. It gets a little bit difficult here because our positive electrode is our anode, will affect our anions. Our negative anode will attract our cations. Our cathode will attract the cations. We need to make sure we remember which way round that is. So the same letters attract each other, but remember an anode is negative and an anode is positive, an anion is negative, and a cathode is negative, but a cation is positive. Now what happens at each of these is we get a case of oxidation and reduction happening. So let's have a little zoom in and look at what's going on a bit later. So our metal atoms form at the cathode. so they're negative electron. They gain electrons to turn from an ion into an atom. So if we look at lithium as an ion, it's got a +1 charge. If we have an electron just floating around and we add them together, and this electron is on our electrode, they're going to produce a lithium atom. This lithium ion has gained an electron, so it has been reduced. We know that from our acronym oil rig. Oxidation is loss, reduction is gain. And we see the same thing happening with any positive ion. It will gain an electron and turn into an atom. Now, our non-metal atoms will do the reverse. They will lose electrons to turn from an ion to an atom, and they've been oxidized. So if we have a look at that, we'll look at chlorine. I'm going to draw the outer shell. So we've got it. It's got a -1 charge. It will get to the positive electrode, and it will want to lose that electron. And what it will then do, obviously, is join up with another one, so that we have a chlorine molecule, and we'll get 2 electrons because we need 2 atoms to come off there. They've been oxidized. So this part here, I needed 2 ions to make one molecule, and I've got 2 electrons out at the end as well. That brings us nicely on to half equations. Now, a half equation shows us what's happening at each electrode. So if we have a look at our anode, our non-metals will lose electrons and oxidation happens. So in my example here, I've had my chlorine ion, my chloride ion, has become Cl2. My oxide ion, so O2 minus, has become O2. And my nitride ion has become N3 minus to N2. If I want to balance this, I need to make sure I've got the same number of atoms on each side. I need to make sure I've got the same number of electrons on each side as well. Now, this one has lost electrons, so it's going to have some spare electrons over here, and it's going to be 2 electrons. So we write 2E minus. The reason why it's 2, each chlorine has lost 1. And for my oxygen, I'm going to have 4 electrons. The reason why, each oxygen has lost 2, and we've got it here. And next one, I'm going to have 6 electrons. The reason why, each nitrogen ion has lost 3 electrons. There's numerous ways we can do this to work out what's going on. We'll put another video up about it later. Now at our cathode, our metals gain electrons. We get the opposite happening. So we have Na+, apologies, that should be Na+, needs to gain 1 electron. Our magnesium needs to gain 2 electrons, and our aluminium needs to gain 3 electrons. What we can do is we can work out what side of the, whether our ion is gaining or losing electrons. If we lose electrons, we've been oxidized. If we gain electrons, we've been reduced. These half equations are tricky. Do have a look at them. We'll put another video up for you to look at. So when we look at the electrolysis of aqueous solutions, so that is where an ionic compound is dissolved in water, not when it's been molten, we get a slightly different pattern. And what we have is we end up having 4 ions being present. We get the 2 from the ionic compound, so our cation and our anion, our positive metal ion and our negative non-metal ion, or polyatomic ions. We also get the H plus and OH minus ions. Now they come from water. Water is H2O, and it splits up into being H plus and OH minus ions, still a positive and a negative. But that means we have 4 different ions floating around in the solution. 2 of them will be attracted to the cathode and 2 will be attracted to the anode. And we only get 1 thing being produced at each one. We're not going to get our hydrogen and our metal being produced at the cathode, and we're not going to get our for oxygen and our non-metal being produced at our anode. Instead, we have some rules that we need to follow. And the rules are very, very simple. If the metal is less reactive than hydrogen, we will form the metal. So we need to think about that reactivity series. Hydrogen will be produced if the metal is more reactive than hydrogen. So, that's the same point. We'll get hydrogen if the metal is more reactive. We'll get the metal if the metal is less reactive. And then for our non-metal, we get oxygen being produced. We get that from the hydroxide ion, unless the other ion is a halogen. So that's our fluorines, chlorine, bromines, iodines, all of those group 7 ones. Then the halogen will be produced. So we've got those rules. 3 rules, really only 2 rules. We're looking at the metal and the hydrogen one is kind of the same one. And then we'll just look at oxygen and the halogen. Let's look at some examples. So what will be produced in the electrolysis of aqueous zinc chloride? So, key part we need to know here. Zinc is more reactive than hydrogen. Because zinc is more reactive than hydrogen, we will produce hydrogen gas. And then we've got chloride, so we'll either get oxygen, unless it's a halogen, and then it's all going to be chlorine. So we're going to get zinc, we're going to get hydrogen and chlorine being produced. Hydrogen, because zinc is more reactive. Now are 3 there for you to try and complete. Work out what the ions are first, and then work out what's going to be produced. So pause the video and give it a go. You should now only be watching if you are ready to see the answers. So our first bit, we've got hydrochloric acid, we've got H plus and Cl minus ions. Now that H plus, well, that is quite an easy one. It's just as reactive as hydrogen. So we're going to form hydrogen gas, and we've got a halogen present, so we're going to form Cl2. And next one, the electrolysis of copper chloride. So we get Cu, and that's going to be a plus, and Cl minus. Now this copper could be 2 plus as well. I'm going to go for plus at the moment because I know it is positive. Now I need to think of which one is more reactive. Now copper is less reactive than hydrogen, therefore copper will be formed. So I'm going to get copper, and then I've still got my chloride ion, so I'm going to get chlorine being formed. And then what will be produced in the electrolysis of sodium nitride, I get Na plus, and I've got N3 minus. Now my sodium is more reactive than hydrogen, so I'm going to get hydrogen being formed, and my nitride. So that's not a halogen, that's from group 5, not from group 7, so I'm going to get oxygen being produced. Well done if you got those correct. If not, go and look at the rules again. So final thing we have is extracting aluminium. Aluminium is incredibly abundant in the Earth's core, but it exists as an ore. Now an ore contains enough metal to make it worth extracting. So it contains enough metal to make it worth extracting. And it often exists as something called bauxite, which is a mixture of all sorts of things, but primarily aluminium oxide. Aluminium oxide is ionic. Because it's ionic, we can split it apart using electrolysis. But its melting point is very, very high. That means it takes a lot of energy to melt it. So we have a high melting point, and that equals lots and lots of money. People don't want to spend lots and lots of money melting it, so we mix it with something called cryolite. And that lowers the melting point. Lower melting point, easier to move. We then have our setup. Now, broadly similar setup, apart from obviously we can now see that our electrodes in slightly different positions. But in here, we're going to have ions, and our aluminium ions are going to be attracted to our cathode. At the cathode, they're going to gain electrons, so we have reduction. What's happening? We're getting aluminium is gaining an electron to become aluminium atoms. We get loads of those. It solidifies or it cools down. We get liquid aluminium and it can be drained out. Now, at our anode, we're going to get oxygen forming. So we'll have O2 minus will become oxygen, just balance it, plus 4E minus. At this stage, we have oxidation. Now, a key thing that will happen is that the oxygen produced here will react with the carbon in the electrodes. When we get carbon plus oxygen, we make carbon dioxide. So eventually, these electrodes need to be replaced. So electrodes need to be replaced. Due to the formation of carbon dioxide. So there we have it, electrolysis done in just under 22 minutes. Thank you very much for listening and good luck with any exams. Take care, bye-bye.